All right, welcome to the first, I think, CGD seminar of this academic year. Uh, so very happy to introduce Dave Bonan. Dave got his PhD about a year ago with Tapio Schneider at Caltech. Very broad thinker about the physics of the climate system, and that's reflected in the title of his dissertation, which is Explicating
Explications.
Explications of a changing climate. So there's a lot underneath that umbrella. And since getting your PhD, you've now joined University of Washington as a postdoc, I think working with Dave Battisti and maybe some others.
Wei Chang.
And Wei Chang. Okay. So take it away. Nice
Cool.
to have you.
Yeah, thanks, Clara, for the introduction, and thanks, everyone, for attending. It's been great to be at UNC. I've been here actually for 2 weeks now, 2.5 weeks. I love it. You can scramble right from the backyard and also do science. It's a really great place to be. But yeah, so today I'm going to give a presentation about work I've been doing kind of since my PhD with Tapio Schneider, but also work with Zhang Xu here. And it's really trying to ask the question of what's the maximum global average precipitation we'd expect to see in a warming world. And so I thought to begin, we would look at what precipitation looks like in today's climate. So we're looking at here is a mean precipitation map from GPCP. This is the Global Precipitation Climatology Project. This is the average precipitation over the past 40 years, essentially. And what you can see is that precipitation is kind of concentrated in this narrow band along the equator. This is the intertropical convergence zone. And then if you look in the extratropics, there's these kind of diffuse patterns that are aligned with this mid-latitude storm tracks. And if you integrate this globally, we end up getting as a value of about 2.7 millimeters per day. And I think what's a bit surprising here is if you look at that over the record, there actually really hasn't been a big change in global mean precipitation. And while you do see kind of some increases maybe aligned with when we see El Nino, like in 1997 or here in 2015, we really haven't seen that large increase of precipitation. And this is a bit surprising in part because if you plot global mean temperature change, which is now from the Berkeley Earth surface temperature data set, what you see is that there's been a pretty steady increase in global warming. And global warming was actually it peaked just last year at a rate of about 1.5 degrees Celsius, which is just past that Paris Climate Agreement. But I think this begs the question of, well, we expect to see an increase in precipitation at about a 1 to 3% per Kelvin. And given this kind of increase that we've seen over the historical or the observational record with no increase in global precipitation, how confident are we in that 1 to 3% per Kelvin scaling? But maybe even more importantly, how much do we trust this 1 to 3% per Kelvin going forward, or looking back at paleoclimates where we've seen kind of warming of about 15 degrees Kelvin as well? And so the way I like to think about this is actually looking at the surface energy budget, and that's just because on timescales longer than a few weeks, global mean evaporation equals global mean precipitation. So this kind of provides a really strong energetic constraint on what we think precipitation looks like, or at least global mean precipitation. And I also want to note that you can link precipitation to the atmospheric energy budget, but I find this a bit more physically intuitive in part because this is how moisture enters the atmosphere. But I want to point to people to a nice paper by Angie Pendergrass and Dennis Hartman that kind of provided this atmospheric energy constraint in a more meaningful way. But the whole point is that you can take this energy budget in the surface, and globally in equilibrium, you know that there's absorbed shortwave radiation, there's some kind of upward longwave flux, there's surface sensible heat flux, and then there's evaporation. And because globally these equal each other, on essentially interannual timescales or longer than a few weeks, we can write out precipitation globally equals evaporation globally, and that's going to be balanced by how much energy is absorbed by the surface and then how much is lost by long wave or surface sensible heat. And so if you go look at this in observations, you can actually just plot or take numbers that are calculated globally. This is actually from a paper from Kevin Trenberth back in 2009. And essentially what you see is that precipitation globally equals evaporation, and this is primarily balanced by the absorbed shortwave radiation at the surface, about 160 watts per meter squared. Most of that is actually lost by long-wave energy, and then some is contributed by the surface sensible heat flux. If you calculate these numbers, you get about 77 watts per meter squared, and if you translate that to millimeters per day, you end up getting that 2.7 millimeters per day. And so if you put observations right here, you can see that this provides a really nice constraint on what we think precipitation looks like globally. And so you can also ask the question, well, how do we get that 1 to 3% per Kelvin scaling? And so you can actually take the surface energy budget, and without even using a climate model or anything, you can kind of get a first order estimate of why we expect to see a 1 to 3% per Kelvin scaling. So again, I'm taking that surface energy budget here. Here's a shortwave energy balanced by long wave and surface sensible heat flux. If you write out the surface sensible heat flux and evaporative flux with the bulk aerodynamic formula, you have these difference between the surface and the near surface of the atmosphere. you have your bulk transfer coefficient, and you have your wind speed. And then for evaporation, it's the saturation-specific humidity. You have some boundary layer temperature or specific humidity that's then balanced with near-surface relative humidity. You have your wind speed, your bulk transfer coefficient. And the whole point is, well, this is kind of a complex set of equations that if we want to just make this a function of temperature, it's pretty hard to do just by looking at this. But if you think about it and you kind of lean on some work of the Penman-Monteith equations, you can actually come up with a nice framework to basically estimate evaporation just based on temperature and get a first-order picture of what we think global mean precipitation will look like going forward in the future. So essentially our goal here is going to be to eliminate the surface sensible heat flux, but also this gradient or this kind of difference in warming between the surface and the atmosphere. And if you do a first-order Taylor series expansion about the saturation-specific humidity, Q star here, you essentially say that Q star at some temperature is going to be a function of that atmospheric temperature, TA, and then this dq dt. And if you stare at that, it's pretty intuitive that this is actually the Clausius-Clapeyron relation, which is essentially this 7% increase in moisture per degree of warming. So that dq dt is essentially alpha times Q star, where alpha is this Clausius-Clapeyron scaling factor. And the whole point of this is that this allows you to kind of linearize around evaporation and essentially approximate evaporation from the saturation-specific humidity with all these different other constants, like relative humidity, the Clausius-Clapeyron relation, the difference between warming, specific humidity, or the bulk transfer coefficient, and the wind speed. And the whole point of this is if you plug this E, this evaporation, back into the energy budget equation, and you also use the bulk formula for surface sensible heat flux, what you end up getting is a formula for global mean precipitation that's based on global mean evaporation that has these different components, where it's eta times essentially the shortwave energy at the surface, or the upward longwave flux, and then kappa, which is essentially all your bulk boundary layer dynamics components. And the reason why this is really neat is eta here is 1/1 plus the Bowen ratio. And this Bowen ratio is at saturation. So you can think of this as a Penman-Monteith equation for a terrestrial evaporation, but a saturated surface, which is what the ocean is. And if you do that, essentially, you can come up with some really nice features where you say, well, suppose going forward in warming, let's just make this a function of T and assume that all these different components here don't change. And what you can do then is calculate the absorbed shortwave flux in today's climate, the upward longwave flux, and then this kappa term, which is essentially all those bulk boundary layer dynamic components. And you can imagine relative humidity globally is about 0.8. We can calculate what the wind speed is. We're going to assume that doesn't change much under warming. And essentially, if you do that, then you can say that precipitation is going to be a function of this term eta here, times this kind of mean component of 123 watts per meter squared. And so this is a kind of first order estimate of if we just plug in temperature here, what's our expected consequence of precipitation as a function of climate state. And this is now global mean precipitation as a function of global mean surface temperature approximated from this kind of scaling here. And if you stare at this, what you see is that there is this kind of 1 to 3% per Kelvin increase from today's climate towards maybe a little bit warmer. But as you go towards these hotter climates, you start to see that precipitation saturates. And it saturates at a value of about 1.25 millimeters per day. And if I just go back to this formula here, the reason it does that is in these hot climates, essentially there's no difference between warming at the surface and the atmosphere. So your surface sensible heat flux goes to 0. If that's true, then your Bowen ratio goes to 0. Eta here is just 1/1, and so it's essentially evaporation is going to be approximated by this constant of 123 watts per meter squared. And so that gives us this kind of peak in precipitation. But I think the important part of it here is tells us that precipitation exhibits weaker increases in warmer climates, and it might actually exhibit a maximum on Earth. And the big question that we've kind of had in this work was, well, do climate models exhibit this behavior? You can imagine that we've assumed here S doesn't change. That could change. Maybe you lose sea ice. Maybe your cloud feedbacks change. That would change how much energy is going to be absorbed at the surface. You're assuming the longwave flux is constant. You're assuming that the wind speed doesn't change. There's a lot of assumptions in this kind of framework here. And so people have already started to begin to think about this. And I want to point people to some work by Paul O'Gorman and Tapio Schneider back in 2008, where essentially they looked at this in an idealized climate model. And what I want to do is reproduce the results and show how you can get from these idealized climate models towards comprehensive models like CSM. And so this idealized model is going to be an aquaplanet. There's going to be no land. It's going to be a slab ocean with a 20-meter mixed layer depth, and there's no heat transport by the ocean. And instead of using really sophisticated radiation, we're going to swap it out for this kind of gray radiation scheme, which essentially just makes your radiative fluxes as a function of temperature alone. And there's a specified solar flux. And then there's no clouds and there's no sea ice. So you can think of this as like your most basic climate model Very simple, but it's a way to kind of test some hypotheses of what would we expect to see based on the scaling. And so if you take this climate model, you can tweak the optical depth of it and start to simulate climate change. And again, I'm plotting global mean temperature as a function of global mean precipitation as a function of global mean temperature. You can see it increases fairly linearly at a rate about 1 to 3% per Kelvin. And essentially for these ranges of surface temperature, there's kind of no state dependence of precipitation. It just increases at that same scaling. But as you tweak the optical depth more and simulate these more extreme kind of hotter house climates, you see that precipitation starts to exhibit that maximum. And so the way you can understand this, again, from the surface energy budget, is that as you go towards this optically thick limit of the atmosphere, your atmosphere is so warm that it's radiating the same energy down as what's being radiated up. There's no difference in temperature. So that means your surface longwave, upward longwave flux is 0, and so is your sensible heat flux. And precipitation is entirely just balanced by shortwave radiation at the surface. And you can then say, well, what's the specified solar radiation in this model? And it actually matches the implied rate of global mean precipitation. And so this tells us there is, again, a fundamental limit that GCMs also suggest should exist. But again, this model is idealized. It contains a lot of several simplifications. There's no land that can modify your surface energy budget. There's no sophisticated atmospheric radiation. You can imagine that would modify how much radiation is absorbed in the atmospheric column. And there's no clouds or no sea ice. And clouds might respond differently and then therefore change how much energy is being put towards the surface. And so that brings me to kind of two questions I want to answer today, which is precipitation really state dependent when simulated with comprehensive GCMs? But what really is the maximum global average precipitation in the world? Can we kind of put a number on what we think the maximum rate of precipitation would be? And so the reason I think this is quite interesting is actually if you look at the paleo record, this is now a reconstruction of global mean surface temperature going back 500 or nearly 500 million years. And what you see is this is a reconstruction from Jim Hansen back in 2013, but then now there's an updated version kind of using modeled observation proxy, Judd et al. And you can see that we go from temperatures of maybe to the present day about 286 Kelvin or 288, down to these glacial cycles of 282 Kelvin. We kind of oscillate between that and the late Pleistocene, and then we go peak back up to these really hot house climates back in the early Eocene. And if you kind of match these numbers here to where those temperatures are, and you go back to this plot here, you can say, how confident are we that this saturation occurs at, say, 315 Kelvin in this model? And would precipitation actually exhibit this peak in the past climates if we're reaching values that are getting close to that? You can imagine that might change if we include clouds, which would change shortwave fluxes to the surface. So it's kind of an important question, and I think more of like a theoretical exercise, but it has implications for understanding paleoclimate as well. And so to answer this, I want to kind of leverage this idea of a climate model hierarchy to build in this complexity and try to understand where can we break this relationship down. So on the y-axis, I'm going to plot comprehensiveness, or the number of components of a climate model, with this being less and this being more up here on the upper part of the y-axis. And on the x-axis is going to be complexity, or the level of detail. Over here is your least complex, least comprehensive model. That was that GCM with the gray radiation. And then we're going to move along this hierarchy to say, well, what happens if we swap out that gray radiation for a more sophisticated radiation scheme, or we include the land surface? What would happen if we include clouds and sea ice? And then kind of moving away from single models, what about all other climate models that are developed across the world? And the way that I'm going to start to plot this is add additional details to each of these plots. But again, what I showed here was global mean precipitation as a function of temperature exhibits this increase, but then it saturates at a certain level of about 6 millimeters per day. And so I'm going to go back to this idealized climate model. And what I didn't tell you before was I ran those simulations, but now I'm running them with the same model, and I'm just going to swap out the radiation scheme. This is actually a really neat framework that was developed by Jeff Vallis in 2018, essentially kind of combining all of these different idealized climate models where you can swap them out with just Python code, and it compiles the Fortran code and allows you to do this. So what I'm using is the model of intermediate complexity, or of idealized moist atmosphere. It's called MEMA. Again, there's a slab ocean, 20-meter mixed layer depth, Q flux, there's no heat transport. But instead of gray radiation, I'm going to swap it out for this RRTM. This is what most climate models use. I'm just going to tweak the atmospheric carbon dioxide value to simulate climate change. But I'm going to form two sets of simulations, one in an aquaplanet and one with a realistic land surface, where the only thing I've changed about the land is there's a different albedo and there's a different heat capacity. So there's no active land processes, but it's really just to say if you had 30% land across the Earth globally. And so if you take that plot of global mean precipitation as a function of temperature, here's the gray radiation model. You saw that increase and it saturates. when you swap out the radiation scheme, you actually see that precipitation increases pretty similarly for most temperatures up to a certain threshold, and it begins to saturate at a lower bound. And it ends up saturating at maybe a value of about 4.5 watts per meter squared, or millimeters per day. And so this really tells us that including sophisticated radiation can change the rate of precipitation increase, but also the mean precipitation peak, or the maximum in precipitation. If we then include that same atmospheric component, but now just swapped out the land surface, you decrease the mean precipitation, and arguably there's very little state dependence in that precipitation at all, right? You can kind of see there's an increase in precipitation. It maybe starts to begin to saturate, but not to the same degree that you see in these interactive aquaplanet, or the interactive radiation in an aquaplanet configuration. And so if we go back to our surface energy budget, we can say precipitation globally equals evaporation. Let's look at how these different components add up to understand more of the processes and the mechanisms contributing to this. And so I told you this earlier. If you plot, so here on the this left plot is the net shortwave radiation. That's the S term. Here's your net longwave flux, and then here's your surface sensible heat flux. You can see that the gray radiation model, essentially there's just the same amount of incoming solar radiation. That's in part because of how it's constructed. Essentially in this model, you prescribe some incoming solar radiation. Some of that's absorbed in the atmosphere, but that doesn't change, and the same amount reaches the surface. So that's a constant as a function of climate here. But in the interactive radiation, you see that strongly decreases as a function of climate state. And I should say there's no clouds in this model, there's no sea ice. So the only thing that's going on here is the atmosphere is containing more water vapor, and it's just absorbing more of that solar radiation in there and preventing it from hitting the surface. And so the way you can start to think about this is as you march towards the state where the atmosphere is optically thick, it's radiating the same energy down from the atmosphere to the surface as what's coming up. Your long wave and your surface sensible heat flux tend to march towards zero. And so precipitation is entirely set by this S term, right? The shortwave energy absorbed at the surface. But because that's decreasing pretty sharply in these simulations, there's a weaker increase in precipitation, but also a different maximum in the precipitation rate. So we can add that now to this kind of hierarchy. We can say, okay, well, we swap out gray radiation for this interactive radiation. We actually see a weaker increase in precipitation and a lower maximum rate. When you include that interactive or that land surface, you actually see that there's very weak state dependence of precipitation, and there might arguably be a 1 to 3% Kelvin scaling across different climate states. So let's include clouds and sea ice. And so for this, I'm going to turn to work that Zhang Chu and Chris Polson were leading back in 2020. And this is actually really neat work where they essentially were looking at the state dependence of equilibrium climate sensitivity. So this is the global mean temperature resulting from a doubling of CO2. And they essentially took different versions of CAM 4, 5, and 6, and essentially doubled CO2 consecutively, but allows you to look at the doubling, or the ECS as a function of the initial climate state. And so if you plot that doubling of CO2, or the temperature change from that doubling of CO2 as a function of the initial state, what you tend to see is that ECS for today's climate, maybe in CAM 4, was about 3 Kelvin. There has been a steady increase for the consecutive versions of CAM 5 and 6. But as you increase that climate state, what you see is ECS is larger as a function of the warmer states. And so this tells us there's some state dependence in how sensitive the climate is to warming, at least in a sophisticated community atmospheric model here. And they attributed this state dependence ECS largely to a strengthening of the shortwave cloud feedback. And if you think about that, that might actually modify the shortwave energy available for the surface. So if we plot global mean precipitation as a function of those same climate states, here's the interactive radiation, but with the land in the idealized model. Here's CAM 4 and 5 and 6. I don't see much state dependence here, right? You can kind of see an increase in precipitation, but it kind of goes at the rate of about 1 to 3% per Kelvin. If anything, maybe this interactive radiation with the land surface actually is the one that has some state dependence, but at least for CAM 4 and 5 and 6, I wouldn't say there's any state dependence in precipitation here. And so I reached out to Zhang about this back in, I think, 2023. And I said, can we extend these simulations to try to understand whether or not there would actually be a peak in precipitation in CAM? And so he was able to run a different set of simulations where we actually started to see precipitation increase pretty linearly, but then kind of max out. And you can kind of imagine this slight kind of maxing out or maybe even decrease is quite interesting, but also you're really pushing the limits of these climate models and lookup tables and the values. So how confident are we that this actually decreases is what we'd expect to see? And Zhang pointed me to a really neat paper by Eric Wolf and Brian Toon back in 2018, or I think this is simulations they performed back in 2015. And they essentially took older version of CAM and changed the radiation code to be a little bit more sophisticated to basically be more precise at these higher temperatures. And they simulated a wide range of climates. And if you plot that global mean precipitation as a function of global mean temperature, you see indeed that precipitation increases pretty linearly. It starts to max out, but then it decreases very strongly as a function of warming. And that's pretty unintuitive. You can imagine if you're in these warm climate states, you're still warming, but your precipitation is going down, which is the opposite of what we'd expect to see. Let's look at the surface energy budget to try to understand, well, what's going on here. So here's precipitation equal to evaporation, shortwave energy, longwave, surface sensible heat flux, same plots as before. This is your S term, your shortwave, this is your longwave, this is your surface sensible heat flux. Those again march towards zero as a function of warming. That makes sense. The atmosphere is becoming optically thick, it's radiating energy back down. There's very little difference in warming between the surface and the atmosphere. But if you look at this Wolf simulation, or at least CAM4 simulation here that was pushed towards these warmer climates, you see that that shortwave energy really does strongly decrease as a function of warming. And that again makes sense, what we talked about earlier, the atmosphere is containing more water vapor, it's just absorbing that shortwave energy and it's preventing it from hitting the surface. And so the way you can start to think about these hothouse climates is that they're just so optically thick, there's no gradient in warming between the surface and the atmosphere, but also just you're not really seeing much because all that energy is just being absorbed in the atmospheric column. And so it really tells us that maybe precipitation does exhibit this maximum in different climates, and maybe it would actually strongly decrease as a function of climate state. So just to reiterate the kind of mechanism that we're proposing here, and I'll talk about that a little bit later in this talk as well. In a warm climate, here's your top of the atmosphere and here's your surface. You have the same amount of energy coming in a warm climate as you do in the hot climate, but essentially the hot climate has so much more water vapor, it's absorbing that shortwave energy, it doesn't reach the surface, and there's therefore weaker evaporation and therefore weaker precipitation. And so we think this is kind of a nice recipe to basically understand what sets the maximum rate of precipitation in hothouse climates, but also it's essentially a nice kind of conceptual picture of what we think sets global mean precipitation in these hothouse climates. So if you plot this now, this GCM with clouds and sea ice, maybe you could argue that we would actually see a decrease in precipitation for these more idealized simulations. We just weren't able to simulate these hotter climates. But these more sophisticated climate models tell us that actually precipitation might exhibit a maximum and it might decrease as a function of warming in these hotter house climates. And if I go back to these plots here, essentially these are all just various versions of CAM4, 5, and 6, which are vastly different models with vastly different physics, but are of the same generation of different climate or atmospheric models. And so this really begs the question, well, what do other GCMs exist? There's over 40 different climate models developed across the world. A lot of them share different components, but what should we expect that maximum precipitation to be as simulated by other climate models? And it's actually a really hard question to answer, in part because running these types of simulations where you're pushing the boundaries of where these models have their lookup tables is just quite difficult, and it's expensive, and it's computationally, it's an interesting state-dependent question, but it's hard to get modeling centers to be excited about performing these simulations. And so I actually took advantage of leverage some existing simulations. This was work from Maria Rugenstein back in 2019 as part of Long Run MIP. She essentially compiled a set of unique simulations where climate models run out to equilibrium, fully coupled back to, I think, sometimes up to 5,000 or 10,000 years. And modeling centers perform sometimes doubling, 4 times, 8 times CO2, so you can really start to look at these state-dependent processes. And I grabbed 2 models that allowed me to kind of maybe start to investigate this. That's the MPI Earth System model and the HAD-CM3 model, which is an older version of HADGEM. And essentially what you see is, if you plot those as a function of global mean precipitation as a function of temperature with these different CAM4 or the Wolf et al. Simulations, they align quite well in these climates relative to today. But if you squint, you can kind of see maybe the MPI model is going to equilibrate at a different value than the CAM model. And it might saturate at a lower surface temperature as well. And so it kind of points to this idea that there might be pretty substantial intermodal spread in global mean precipitation in these hothouse climates. And so what I want to do is propose a very simple analytical model that can actually approximate that global mean precipitation in these hothouse climates via this very simple recipe. And the idea is that from the surface energy budget, we know that shortwave energy in hothouse climates, essentially there's no longwave and sensible heat flux. So if you can estimate where that goes to 0, and you had some approximation for what S is here, the shortwave radiation, you can approximate what that maximum precipitation is. And so I'm going to rewrite this L and H term as just F. So it's going to be S minus F. And I'm going to say, let's solve for temperature when F is 0, and let's plug in that temperature for some approximation for S and solve for the maximum precipitation. Okay, so we can leverage these existing simulations that Eric Wolf and Brian Toon ran. And that's what I'm plotting here now is F as a function of surface temperature. This is from that climate model. This is essentially CAM4 and a slight variant of that. And what we're going to propose is this kind of functional form of F equals F sub C, which is essentially the mean component of this curve. And there's going to be this tangent component. And the whole point of this is that if you look at this plot, there's a pretty linear space here where it increases as a function of temperature, but it saturates at a higher temperature. And so you can do a Taylor series expansion of this F equation. And essentially what you get is F as a function of T is, again, that mean component F sub C. There's going to be this linear component, which essentially is how does F change as a function of temperature? So it's delta sub F, delta sub T. If you stare at this kind of just looks like a regression coefficient, right? So we can estimate what that term is based on this kind of regression here. And then there's these higher order terms that just capture where that begins to saturate. And the whole point of this is you can write out a very simple equation that just says, let's approximate the long wave and surface sensible heat flux as a function of temperature in a linear form. So it's A plus B times T, essentially. And you can fit this model. If you just take a pre-industrial control simulation and a 4 times CO2, you can fit this model and then approximate the long wave flux as a function of temperature. So what's neat is I don't need all these different simulations to get these coefficients. I just need a pre-industrial control and a 4 times CO2, which is what most modeling centers provide as part of the standard CMIP output. And if you look at this, you can see this red line approximates it quite well. It approximates it precisely when it goes past 0, but it also kind of captures that saturation. So this tells us that the long wave flux and surface sensible heat flux are taken care of. The shortwave component is a little bit more complicated, in part because there's going to be here, we're going to break it up into a cloud component, but also this clear sky term. And so there's no satisfactory way to approximate the shortwave cloud effect analytically. So we're just going to, again, make that a function of regression coefficients. So I'm just going to call it A plus B times T, but these are going to be cloud radiative effects. But for the clear sky term, it's actually a little bit cleaner and a lot nicer to work with. And that's in part because you can write out this clear sky term as 1 minus the albedo, 1 minus the albedo times the downward component of the shortwave clear sky term. And the whole point is in these hothouse climates, the albedos are actually relatively constant. They have no ice, so it's really just whatever the land surface was set to and whatever the ocean was set to. And at least in these idealized CAM simulations, the land surface albedo doesn't change. There's no forest die-off or anything, and the albedo is really just set by the ocean. So that's going to be set to 0.07, which is what we'd expect it to be over the ocean domain. And if that's true, then all we need to do is really come up with a functional form of this clear sky term as a function of temperature. And so we're going to approximate that surface term as the difference between what's coming in at the top of the atmosphere and what's absorbed within the atmosphere column. So that's S downward TA minus S downward clear sky absorbed in the atmosphere. And for the atmosphere, we can actually turn to a really nice paper by Ben Fielder and Bill Collins back in 2015, essentially where they showed that most climate models, you can actually approximate the clear sky, the shortwave radiation that's absorbed in the atmosphere as a function of clear sky radiation with this simple form. And so what this form is telling us is, first, there's an optical depth. There's going to be some kind of optical depth of the atmosphere. Mu here is the cosine of the zenith angle. Globally, that's just going to be set to a constant. It's pretty easy to approximate. And then there's going to be some kind of incoming solar radiation that's absorbed in the atmosphere in today's climate, S sub C. And then eta here is going to be your kind of maximum fraction at which you could absorb, just to kind of understand if a model's radiative transfer scheme, or to kind of capture the intermodal spread in a model's radiative transfer scheme. And you can take this optical depth and actually just make it a function of precipitable water, where you have this kind of water vapor absorption coefficient kappa here, and then an absorber for all other factors like CO2 or methane or whatever it has to be. But precipitable water actually scales like the Clausius Clapeyron relation, which is again that 7% per Kelvin scaling. So we can write out now precipitable water as a function of temperature according to this analytical formula. And the whole point is that now we've approximated precipitable water. That makes this optical depth as a function of temperature. We plug that into our shortwave clear sky formula that absorbed in the atmosphere. And we essentially have a closed form solution that approximates the shortwave energy just as a function of temperature. If you do that, and again, only use pre-industrial control simulations and abrupt 4 times CO2 to calibrate this simple model, you can essentially approximate that entire structure of the shortwave radiation just from the simple model. And you can see, so the 2 points, there's shortwave energy as a clear sky and a cloud. The cloud component is this simple regression model, and the clear sky is a little bit more complex, but it just essentially means water vapor absorption is scaled along the 7% per Kelvin based on precipitable water. And you can see there's some deviations, especially in this hotter climates. Essentially what's going on there is there's a lot of pressure broadening that we're not capturing. This is very simple. And if you go towards these colder climates, we're not capturing the fact that the albedo might change because of a sea ice feedback or anything like that. But if you just use a constant albedo from the hothouse climate and do that, you actually capture most of that structure quite well. And so I think what's really neat about this is it basically tells us, okay, we can approximate where that long wave flux goes to 0, plug that temperature into the shortwave approximation, and get what the maximum precipitation is. And so here's our recipe. Take that formula for F, solve for when it's equal to 0. You essentially get this T, what I'm calling T star. I put a tilde over here because I'm estimating it. We're not actually simulating what the temperature is, but we're going to estimate it. And essentially, that's going to be primarily determined by this A and B coefficient, how sensitive your long wave fluxes are to warming. And then we're going to plug that T into this formula for S, which I'm going to call P max, because where precipitation is going to, or where the long wave flux goes to 0, precipitation is going to be constrained by shortwave energy, and that's going to be your maximum precip. And because that's a function of just temperature alone, this allows us to approximate the absorbed shortwave radiation. And so I'm kind of walking through this fairly quickly, but I basically want to argue that this is a very simple recipe to estimate what the maximum precipitation is in these hothouse climates. But there's a number of parameters you need to calibrate this model to. So use your sensitivity of long wave fluxes to warming. This is A over B. You have your absorbed shortwave radiation in the atmospheric column. Maybe there's this eta parameter of how much maximum solar radiation you could actually absorb. Every model is going to have a different kappa coefficient, how sensitive that shortwave energy is absorbed to the kind of water vapor that's present in the atmosphere. There's going to be all other absorbers, and then there's this cloud component. And so you need to really calibrate this model to all different climate models, but the whole point was, let's write it in a way where we can use existing simulations like the pre-industrial control or an abrupt forward times CO2. What's also really neat is Eric Wolf and Brian Toon ran a set of CAM4 simulations that not only examined the sensitivity of CO2, but different solar constants as well. So it really gives us this kind of phase space to estimate what the maximum precipitation is as a function of these different climate states. And so what I'm showing here now is global mean precipitation as a function of temperature. But for the simulations I showed before in orange, that was the same solar constant that we use in climate models today. They've increased it by 10%, that's the green simulation. They decreased it by 25%, that's the blue simulation. And essentially what you can see is that global mean precipitation exhibits stronger maxima as you increase that solar constant, but it also peaks at a higher temperature as well. And so if you calculate this T star term in the model, you can see that for solar constant reduced by, say, 25%, it goes to 325 Kelvin, at least in CAM4. Whereas if you go to a model or a simulation in which the solar constant was 10% stronger, you'd actually exhibit that peak at 335 Kelvin. But that peak maximum is also stronger. So there's 5.2 millimeters per day in this simulation, whereas in the constant that's 25%, or the solar constant that's 25% lower, it's 3.67 millimeters per day. But the whole point is, can we take these simulations, we know where these T star and P max are, and calibrate our simple model just to kind of simulations that we have readily available today, like the pre-industrial control and the abrupt forward time CO2, and essentially emulate those T stars and P max. And so the way we're going to do that is, again, just take these abrupt forward time CO2 simulations. And what I'm going to show here is just the parameters that I calibrate uniquely to each different climate model. Essentially, what we found is that these can be constant regardless of the simulation you're using. So this just says the temperature at which you begin to exhibit that saturation, and here's the temperature space at which you should exhibit a saturation. But you can calculate the A and B in this climatological T term here by just saying, here's surface temperature, here's that F term under an abrupt forward time CO2. Let's get the regression coefficients. Now we have this analytical formula to approximate what F is as a function of T. The clear sky term or the shortwave term is a little bit more complicated. I'll start by just saying the cloud formula is the same as essentially the long wave is surface sensible heat flux. We just get regression coefficients from the cloud rate effect as a function of temperature. That gives us alpha and beta here. And then for the clear sky term, we actually just take this absorbed clear sky in the atmosphere and say, and that's in gray here, for a climate model under abrupt forward time CO2. This is a 150-year simulation. And what we do is prescribe precipitable water in today's climate. We assume it scales like 7% per Kelvin. We have our mu coefficient, and we have these kind of incoming solar radiation constants. And essentially, if you do that, you can then just kind of iteratively fit that model and get the coefficients that you need to satisfy the clear sky absorption. And I think what's just pretty surprising is, this is also work that Bill Collins noted early in the 2000s, is that this is just a simple model, essentially estimate the shortwave absorption of any climate model. And so you get these coefficients. You have today's climate is about 93 watts per meter squared is absorbed in today's climate for shortwave radiation under clear sky. Here's the mean temperature today. Here's the precipitable water today. Here's your radiative transfer coefficients, essentially emulating that climate model's radiative transfer. And then here's your shortwave cloud term. So we have that simple recipe. We have these different parameters. We can plug all that in to these vastly different climate models, but also first to validate against the solar constants that Brian Toon and Eric Wolf had run. And essentially we can say, let's approximate T star, plug it into this approximation for S and get P max. And if you do that, you actually get a nearly one-to-one relationship. So on the x-axis is the simple model's estimate of where that surface temperature goes to 0, or where the longwave flux goes to 0. And here's the surface temperature as simulated by that GCM. And here are these different solar constants and simulations. And essentially we approximate that on that one-to-one line pretty remarkably well, just from a pre-industrial control and a abrupt 4 times CO2 simulation. And then we plug that into our P max, and we actually also approximate that quite well on this one-to-one line. So it tells us that to estimate what this maximum precipitation is as a function of climate model, all we need to know is to calibrate those two different equations to these different climate models, and we can perform this across all available climate models across the world. And I think what's really neat too is it also, well, I'll go into this a little bit later, but it reformulates the surface energy budget purely as a function of temperature, and I think it opens up a lot of other really interesting questions. But now let's go back to these simulations from the MPI air system model, the HAD-CM3 model, and this inspiration that, well, actually they might saturate at a lower temperature, and they might exhibit a lower peak. And what's the reasons why that might happen? And so if you go take every single CMIP6 model, I think this is now 46 different model simulations from abrupt 4 times CO2 and pre-industrial control, and I calibrate the analytical model. Here is the distribution of surface temperature at which the longwave flux goes to 0. You can see that ranges now from, say, about 300 Kelvin all the way up to 350 Kelvin. And I can plug that temperature in for the analytical model and essentially get the precipitation maximum, and that's going to be ranged now from 3 millimeters per day all the way up to 9 millimeters per day. So first, I think this is neat, but two, that's a huge intermodel spread, and I don't know if we have any confidence of which component or what's going on here, or what should we trust? Should we say the maximum is 8 millimeters per day or somewhere between there, or is it 3 millimeters per day? So to start to kind of understand the sources of that spread or what's contributing to the spread, we can break it up into our two different terms. So this term one right here is the clear sky term. That was the shortwave approximation that I've came up with the analytical model. And here's the cloud rate of effect, which is just that linear regression component. And you can see that models actually are pretty certain that the maximum precipitation as implied by clear sky radiation is going to be somewhere between, say, 6 and 8 millimeters per day. But most of that spread that kind of gives you that width of that distribution is coming from the shortwave cloud rate effect, which probably isn't too surprising, in part because that's one of the most uncertain aspects of climate models under forced change. But essentially 70% of the spread comes from the cloud component, and 30% is going to come from this clear sky component. And the way I like to think about this, that I've been pitching it to people, is that without shortwave cloud rate effects, there really is a fundamental limit on what precipitation is in today's climate, or not today's climate, on Earth. And so if you were to keep consecutively doubling CO2, we should expect that to max out at about 8 millimeters per day and go no higher. What's really neat about this framework is it allows you to come up with sources of intermodal spread that can be attributed to both the radiative components of models, but clouds, and the base state of the climate as well. So this top panel is going to show the clear sky term, which is term 1. And I've essentially just said, let's approximate term 1 with the intermodal spread of all these different mean state components. So like precipitable water today, the temperature today, the solar constant. That only contributes maybe 30% of the intermodal spread, whereas the majority of the spread actually comes from the radiative transfer coefficients here. So this is eta, kappa, and tau, which essentially is just how sensitive your radiative transfer code is to that precipitable water. And most of that spread is actually coming from that. So the clear sky term can be entirely attributed really just to the intermodal spread of the radiative transfer scheme. And if you take the cloud component, you can do the same exercise of just plotting the intermodal spread of term 2 against the intermodal spread of these different terms, where the others are set to the multi-model mean. And essentially most of that spread, again, is from the sensitivity of that the shortwave cloud response to warming. And I don't think that's too surprising, but the whole point here is that if we can start to constrain what this value is in across climate models, we can start to better constrain what that estimate of the maximum precipitation is, but also kind of, if you can constrain your radiative transfer model scheme in today's climate, you might also be able to reduce the intermodal spread and essentially this maximum precipitation. And so to summarize, I just want to say the response to precipitation to climate change does depend on the background state. in these hot climates, global mean precipitation really does cease to increase with warming, and it actually might even begin to decrease. This occurs because the atmosphere becomes optically thick. Precipitation is entirely balanced by shortwave radiation at the surface, but because your atmosphere holds more water vapor, you're going to absorb more of that radiation in the atmospheric column, and that's going to limit evaporation and therefore limit global mean precipitation. And this simple analytical model can really be used to estimate what the maximum mean precipitation in hothouse climates might be. And we showed that ranges between, say, 300 and 350 Kelvin and 3 and 9 millimeters per day. But I wanted to really end with some broader implications here is that I think there really is a fundamental limit on what global mean precipitation could possibly be on Earth. Again, that ranges between 3 and 9 millimeters per day, which is pretty unsatisfactory amount of intermodal spread. But the point is that there now might be actually an upper limit on what precipitation might be of about 9 millimeters per day. And I think these results actually have some interesting context for understanding paleo applications, especially at warm periods like the early Eocene. So I showed this plot earlier of global mean temperature going back 500 million years. And what you can see is that there's periods where temperature reaches maybe above 300 Kelvin all the way up to maybe 315 Kelvin. And if we were to trust those lower ends of these models, we might actually say global mean precipitation exhibited that peak in the past. But you can imagine there's a lot of other things that go on in these past climates. You might alter the land-ocean geometry that would alter your surface fluxes. Clouds might respond vastly different. You might actually have interactive land where forests die off and there might be changes in albedo, so we don't capture that. But I think a lot of really interesting future work could explore this, at least in understanding paleo applications. But I think some of the more fun stuff that we did here too was we reformulated components of the surface energy budget just to be a function of temperature. And so if you combine these approximations with other approximations from like idealized energy balance models or diffusive heat transport, you can really start to understand a wide range of processes in physics in the hot and cold climates, especially around heat transport or spatial patterns of the hydrologic change like P minus E. And so I think there's kind of some broader implications of writing out the energy budget in this way as well. So just wanted to end by saying thanks, but these have been written up, one paper back published in GRL just last year, and then one I'm currently in prep about to submit to Journal of Climate. So happy to take any questions.
For questions in the room and online. Yeah.
Oh, mic's good?
Yeah, mics are good, right?
I mean,
yeah.
All these kind of global metrics really does, and the variation, it does beg the question, what is happening kind of regionally? If you look at these, you're getting plus 8 millimeters per day, and I'm just intrigued, is that all in the ITCZ mid latitudes?
No, yeah,
globally?
It's a great question. So in our GRL paper, we actually looked at it regionally, and essentially you see a decrease in global mean precipitation, or in precipitation in the tropics, and decreases in the subtropics, but the extratropics continuously get wetter, despite there being decreases. Yeah, so there's really strong regional variations to this. It has implications for like precipitation variability and like episodic precipitation. So yeah, I think that would be fun to explore, but yeah.
I had the same question. Any other questions? I'll take another one in the room. Katie.
Nice talk. I'm curious about the idea of running the climate models at very high temperatures. So you mentioned this concept of lookup tables a couple times. So can you say more what you mean about that? And the Wolf et al. Study seems very unique in that.
Yeah.
It's one of the only ones that was able to run at those higher temperatures.
Yeah, I can't speak entirely for the Wolf study. I know what they did is they swapped out the radiation scheme to be a more sophisticated radiation scheme that was more precise for those high temperatures. But an example would be, if I could go back, I don't know if I can, but to the MEMA simulations I was running, that was using RRTM, but with the lookup tables essentially just kind of become invalid at a certain temperature. So I've actually been telling a bunch of people this. I used ChatGPT to essentially like expand along the lookup table, and I was able to alter that Fortran code to make that more sophisticated. But another example of this was simulations that Zhang Chu ran. If you go essentially ran past a certain global mean temperature, I think there was a convective term that just like was past some lookup table and the model crashed. And so I think, you can imagine with all these different modeling centers, there's going to be a vastly different set of ranges where you can do this, and so it might not even be possible. But I think it'd be great for modeling centers to maybe, even just in an atmospheric model, which is maybe a little bit more computationally cheap than a fully coupled model, to explore the state dependence. And this motivates that work.
Right.
this is maybe related to Osamu's question that will come up next,
Yeah.
but I really like the constraint using the global average surface budget. Another constraint that people have used is to assume that the relative humidity doesn't change very much. And I
Yeah.
wonder, one, what you think of that as a constraint, and two, if you think if it's valid, then could it constrain the shortwave cloud effect?
Totally. I haven't thought about applying. I know there's actually, I should say, like when this paper was published, there was actually a similar paper published by a different group of showing the same behavior in a different set of models, and they did the other constraint and showed it worked. So that validates it. But I haven't thought too much, I guess, about whether you could, yeah, that would be a nice way to constrain the shortwave cloud component, yeah. I'd have to think about it some more.
Okay, great. So maybe we'll take Osamu's question and then we'll take the more in the room. Do I read the question? Is that, okay. Have you considered including cloud resolving models in your model hierarchy?
So I would love that if there were the resources, I think, to be able to do it across these different states, especially on the global domain. Part of this work was inspired by a set of researchers at Harvard that were actually doing this in a cloud resolving framework, but an idealized domain. And essentially they simulated these warm hothouse climates and showed that you get episodic deluges of precipitation. Essentially you can imagine this looking, if precipitable water goes up, you have more water vapor in the atmosphere, but your mean precipitation goes down. The residence time of water vapor is longer. That could imply that precipitation has the same mean for two different states, but it's just these big, intense bursts of precipitation. And I know that they're focused on that, but I don't know of anyone I don't even know how it would be possible fully to do a cloud resolving model in a global domain like this, especially these point range, but I could, yeah, defer to the atmospheric people. It'd be cool, yeah.
Keith.
Nice analysis, Dave. Some of this depends upon the composition of the atmosphere, like that mostly N2. Then you're referring to some deep time paleo.
Yeah.
Do we know much about the composition of the atmosphere billions of years ago?
Jean, do you want to answer that? But yeah, I don't know.
I think at least for the time series you showed the last maybe 500 million years,
Yeah.
The composition shouldn't be too different.
Yeah. Yeah, I think like in our paper we had written that there's implications for understanding the Archean and Hadean eons, but I mean at that point the composition is so vastly different that it might be new to apply this framework, but yeah, that's a good question.
Dan.
Yeah, staying in deep time, so on millions of years timescales, the carbonate silicate weathering rate is an important feedback on CO2 concentrations in the atmosphere.
Yeah.
And as I just reminded myself from Wikipedia, that increases as a function of temperature, and also as a function of precipitation.
Yeah.
So is that a constraint that you could use that we have not entered a runaway greenhouse to try and
Yeah,
keep
totally.
down these numbers?
Yeah, I actually think that totally could be I gave this talk, like a version of this talk elsewhere, and that was the same question that kind of came up, and I think it would totally be a constraint on preventing that runaway greenhouse, runaway hothouse climate. Yeah.
Any other questions? Yes.
It's a Lee one. Does the phase of the precipitation matter? I mean, at some point, I guess the snow is gonna go away.
Yeah. No, yeah, this is, I mean, I actually didn't break it up in like the convective and large scale component like at all, but I would assume that this behavior could change vastly if you had cloud resolving models in the convective, I don't know. So I think there's a lot more to investigate there, but I think the way I like to, I mean, you can imagine it from this perspective of everything's gonna balance each other, but what we've essentially just done is applied the Penman-Monteith equation to like, you know, long-term climate, but we're not really looking at the dynamics of precipitation at all either. So I think there's a lot more to do here, yeah.
Okay, let's thank Dave again. Thanks.